Okay, so my name is Alexey Yulievich Pirkovskii, and I'll give you lectures in functional analysis. Since we have some international students registered for this course, the lectures will be in English. And here are my contacts. Okay, so first of all, let's discuss our plans, some organizational issues. I will make a web page of the course within a few days, and I will put there some relevant information. For example, there will be a detailed description of the grading rules. There will be a brief description of each lecture, just a few lines for each lecture. There will be some references to textbooks. There will be contacts of instructors and of teaching assistants. And of course, there will be exercise sheets. By the way, a few words about exercise sheets. So we will have two types of exercise classes, namely traditional seminars, I mean Russian-style seminars, when you discuss solutions of exercises together with the instructor at the blackboard. And we will have, let's say, individual problem discussion, that is прием задач from exercise sheets. And usually we will alternate. So, for example, today we'll have a traditional seminar, and the next week we will have individual problem discussion. Also, we'll have two groups. So the first group, two groups for exercise classes. So the first group will be today, right after the lecture, and the second group will be on Monday. I don't remember exactly the time. So the instructor of the first group is Professor Rovinsky, and the instructor of the second group is Professor Shilin. So you have just to choose which time is more convenient to you, and you're welcome to attend. Well, maybe that's all about some general stuff. Let me now say a few words about the subject we are going to learn. There are many opinions on what functional analysis is. Probably the most general opinion is that functional analysis studies spaces equipped with compatible algebraic and topological structures. And to get some feeling on what it means, let's look at the following toy example. So let's consider the space Rn, which you are probably familiar with since your kindergarten. So Rn consists of ordered n tuples of real numbers, x1 to xn. So what can we say about this space? Well, first of all, we know from our linear algebra course that this is a vector space over the field of real numbers. So the algebraic operators are defined component-wise in the standard way. Second, we know that this space, Rn, has a canonical topology. So it is a topological space. And moreover, the canonical topology on Rn is compatible with the vector space structure in the sense that the algebraic operations are continuous. And this means that Rn is a topological vector space. That is a vector space equipped with a topology such that the operations, the algebraic operations, are continuous. Moreover, we know that the canonical topology on Rn is given by the so-called Euclidean norm. The Euclidean norm on Rn is defined by the following standard formula. The Euclidean norm, or the Euclidean length of a vector x, is given by this formula. And this norm determines a metric on Rn. The metric, the Euclidean metric, is given by the following formula. Since this is a metric, it determines a topology. And this is precisely the canonical topology on Rn. I will comment on the subscript 2 a bit later. So this is just a standard notation for the Euclidean norm. Okay. So what does that mean? This means that Rn is not just a topological vector space. This is a normed space. A vector space equipped with a norm. And this norm determines a topology. Also, you probably know that Rn is complete in the sense that each Cauchy sequence converges. And this means that Rn is a Banach space. A Banach space is a complete normed space. And finally, we know that there is a canonical inner product on Rn. Inner product in Russian is скалярное произведение. So the standard inner product on Rn is given by the following formula. And this inner product determines the Euclidean norm in the sense that the Euclidean norm is related to the inner product by the following rule. So the norm is the square root of the inner product of x by itself. And this means that Rn is not just a Banach space, it's a Hilbert space. Usually Hilbert spaces are defined over the complex numbers, so this is a simple example of a real Hilbert space. To some extent, this example illustrates what we are going to study, but nevertheless it is too simple in the sense that because it is finite dimensional. In fact, most interesting spaces studied in functional analysis are infinite dimensional. And I'll give you some examples in a few minutes. Apart from various spaces, functional analysis studies operators between such spaces. And in fact, operators are often even more important than the spaces on which they act. Sometimes spaces, functional analytic spaces, are specially constructed in order to study operators of a certain type. And perhaps the most famous example of such spaces are the Sobolev spaces, which are the natural home for differential operators. Now just a few words about the history of the subject. The classical functional analysis was created in the first half of the 20th century in the works of Hilbert, Schmidt, Ries, Banach, Weil, von Neumann, and by many other brilliant mathematicians. In spite of the abstract nature of the subject, it has grown out of some very practical and concrete areas, such as approximation theory, solving equations in function spaces, the theory of trigonometric Fourier series, and so on. And the modern functional analysis is a rather vast subject, and it has numerous applications in other fields of mathematics and physics, for example, in geometry and topology, differential equations, harmonic analysis, representation theory, optimization, quantum physics, and so on. Okay, so this was a short introduction. And now let's introduce our main objects. So today, our main objects will be normed spaces. We will work over the field of real numbers or the field of complex numbers. And in most cases, it is not essential for us which of them is our base field. So we will use the following notation. I will write the symbol, bold K, to denote any of these two fields. So this is either the field of real numbers or the field of complex numbers. This is our base field. Okay, so suppose now that we have a vector space X, a vector space over K. And we give the following definition. A norm on X is a function, a non-negative real function on X, which takes each element little x to a non-negative number, denoted like this. So this is the norm of the vector x, such that the following axioms are satisfied. First of all, we have the triangle inequality expressed by the following formula. Second, our norm is homogeneous in a suitable sense. More exactly, the following identity holds for each lambda and each x in our space, for each number lambda and for each vector x. In particular, this formula easily implies that the norm of the zero vector is 0. And axiom 3 says that the norm of any non-zero vector is strictly positive. So if these properties hold, then we say that this function is a norm. And the vector space X equipped with a norm, or more exactly a pair consisting of a vector space and the norm on the space, is called a normed space. Sometimes we will meet functions which satisfy conditions 1 and 2, but which don't satisfy condition 3. So if only conditions 1 and 2 are satisfied, then we say that this function is a semi-norm on X. So roughly, a semi-norm is a norm which is allowed to vanish on non-zero vectors. And a vector space equipped with a semi-norm is called a semi-normed space. So we will meet such spaces occasionally, but they are not very important for this introductory course. So we will be interested mostly in normed spaces. Okay, let's now observe that if we have a normed space, then the norm determines a metric in the following standard way. So the norm of x minus y is the distance between x and y. And this is a metric on X. So each normed space carries a canonical metric, and this metric determines the topology in the standard way. So in particular, each normed space becomes a topological space. Okay, let's now look at some examples of norm spaces. First of all, let's observe that the field K itself is a norm space over itself. And the norm is just the absolute value. So this is a norm space. And by the way, it's easy to deduce from our axioms that this is essentially the only norm on K that is the only norm up to a multiplicative constant. Example 2 is more interesting. Let's now look at the finite dimensional space Kn, and let's try to construct some norms on the space. Norms on Kn. Well, first of all, we have the standard Euclidean norm given by the following formula. So if K is the field of real numbers, of course, I can just take the sum of the squares here, but in the complex case, I have to put the absolute value here. Well, this is indeed a norm. It's obvious that it satisfies conditions 2 and 3. The triangle inequality is not entirely obvious, but it is absolutely standard, so you probably know it from your geometry course. In fact, we have several natural choices for a norm on Kn. Another natural choice is just to take the sum of the absolute values of the coordinates. And this is a different norm on Kn. And it's clear that all the axioms are satisfied. So this is also a norm. Another choice is just to take the maximum of the coordinates, the maximum of the absolute values of the coordinates. And again, this is a norm. All the axioms are easily verified. And this norm is denoted like this. In fact, these three norms on Kn fit into a family of norms indexed by a real number p greater than or equal to 1. So for each real number p greater than or equal to 1, we can define a norm denoted like this. This is a norm on Kn given by the following formula. In particular, if p equals 2, then we get the Euclidean norm. Why is it a norm? Well, again, axioms 2 and 3 are immediate. And the triangle inequality is not entirely obvious. In fact, the triangle inequality for this norm is the famous Pirkovskii inequality. I will not prove it now. The proof is included in our first exercise sheet. So we will probably discuss it at the exercise classes. So now let's just take it for granted that the fact that this norm is indeed a norm. It satisfies the triangle inequality. Okay, so we have that. We see from this example, we see that there is a whole family of interesting family of norms on Kn, and if n is bigger than 1, then all of them are different. Of course, if n equals 1, then we get this norm. But if n is at least 2, then all of them are different. Okay, let's now look at something infinite dimensional. An important group of infinite dimensional norm spaces consists of sequence spaces. First of all, let's introduce the following notation. The space of all k-valued sequences will be denoted by k to the power n. This is the standard notation for the space of all sequences from K. Of course, this is a vector space under the component-wise operations, but this is not a normed space. So it doesn't have any natural reasonable norm. However, it contains many interesting normed subspaces. So example 3. As above, we denote by p any real number greater than or equal to 1. And we denote by little p the set of those elements, of those sequences, of those elements in Kn, for which the following series converges. So what can we say about this space? It's easy to see that if we use the Pirkovskii inequality, then we can easily deduce that, first of all, this is not just a set, but this is a vector subspace in Kn. Lp is a vector subspace in Kn. And second, the space has a natural norm given by the following formula. So this is a normed space. Lp is a normed space. Well, to deduce 1 and 2 from the Pirkovskii inequality, we just take two elements in Lp and write the Pirkovskii inequality for the finite sums from 1 to n, for the finite dimensional space Kn. And then we just let n go to infinity. And using this, we see that the sum of two elements from Lp is again in Lp, so it's a vector subspace of Kn. And we also see from this that this norm satisfies the triangle inequality. Of course, if p equals 1, then this is trivial. Probably the most important space in this example is the space little L2, because it's a standard example of an infinite dimensional Hilbert space. But today we will not discuss Hilbert spaces. This will be done maybe in 2 to 3 weeks. Another natural example of a normed sequence space is the space of all bounded sequences. This is example 4. The space of all bounded sequences is denoted by little L infinity. This is the space of those k-valued sequences which are bounded. Clearly, this is a vector subspace of Kn, and there is a canonical norm on this space given by the following formula. This is a norm on L infinity. So this is the infinite dimensional version of Kn equipped with this norm. The space little infinity contains a useful subspace. This is example 5. So we denote by little c0 the space of those sequences which vanish at infinity. So this limit is 0. Well, clearly this is a vector subspace of L infinity. If a sequence vanishes at infinity, then of course it is bounded. So C0 is a vector subspace of L infinity. And so it is a norm space under the supremum norm. Okay, so these are the basic example of sequence spaces. The next group of examples is actually, it is more general, and it consists of so-called function spaces. So if you have a set, if X is any set, then the space of all k-valued functions on X will be denoted by k to the power x. So this is the standard notation for the space of all functions on X from X to k. Well, of course, this is a vector space, but it doesn't have any canonical norm unless X is finite. Of course, if X is finite, then this space is just Kn, where n is the cardinality of X. But if X is infinite, then the space doesn't have any reasonable norm. So we will be interested in some vector subspaces of k to the power x. Example 6. Example 6 generalizes example 4. So we can consider the space of all bounded functions on X. And this space is denoted little L infinity of X. This is the space of all bounded functions on X. So this is a vector subspace of k to the power x. And it has a canonical norm, which is just the supremum of f of x, or the absolute value of f of x over our set. This is the so-called supremum norm or the uniform norm. And by the way, the convergence of sequences with respect to this norm is just the uniform convergence, which you know from your calculus course. Example 7. Suppose now that X is not just a set, but is a topological space. In this case, we can consider the space denoted by CB of X, which consists of all bounded continuous functions. F is continuous and bounded. So in other words, this is just the intersection of little infinity of x with the space C of x of continuous functions. And since this is a vector subspace of little infinity, it is also a normed space. This is a normed space under the supremum norm. And an important special case of this example is the case where x is compact. If x is compact, then we know that all continuous functions on x are bounded, and so CB of x is just the space C of x of all continuous functions on x. So it is a normed space. But if x is not compact, then in general, C of x doesn't carry any canonical norm. Well, now let's now look at a useful space of differentiable functions. Example 8. Let's consider the space Cn of AB of n times continuously differentiable functions on a closed interval of the real line. And of course, this is a vector space. And we can, for example, consider it as a subspace of C of AB. Well, C of AB is a normed space by this example. And so Cn of AB also becomes a normed space under the supremum norm. But this is not a good choice. The standard norm on the space Cn of AB is given by the following formula. So for each derivative of f from 0 to n, we calculate the supremum norm of this derivative and then take the maximum of all these numbers. So we get a norm, and this is exactly the standard norm on Cn of AB. Why is it standard? Well, first of all, this norm takes into account the differentiability properties of our function. And what is more important, we will see soon that this space is complete under this standard norm. And on the other hand, it is not complete under the supremum norm. Okay. Well, now before we proceed with examples, let's discuss, let's make a short digression and discuss a general construction which will enable us to construct normed spaces out of semi-normed spaces. So a general construction. Suppose that we have a semi-normed space, X. It is a vector space equipped with a semi-norm. And let's denote by n the set of those vectors, x, for which the semi-norm of x is 0. And let's observe that the triangle inequality easily implies that n is actually a vector subspace of x. So we can consider the quotient of x modulo n. And it turns out that we can easily define a norm on this quotient as follows. So to distinguish between this new norm and this semi-norm, I'll put a check here, a hat. So this will be a norm on the quotient of x modulo n. And this norm is given by the following simple formula. So if we take an element of the quotient, that is a coset of x little x modulo n, so the norm of this element will be just the semi-norm of any representative. It's a simple exercise which is included in our first exercise sheet to show that this is well defined, that is, it doesn't depend on the choice of a representative. And this is a well-defined norm. This is a well-defined norm on the quotient. This is a simple exercise. So we see that the quotient of x modulo this subspace n becomes a norm space. And the space is called the norm space associated to x. So this is the standard method of constructing norm spaces out of semi-norm spaces. Okay, now let's come back to examples. Example 9. Suppose that we have a measure space, x mu. So let's recall that formally a measure space is not a pair, but is a triple consisting of a set x, a sigma algebra of subsets of x. So I don't introduce any special notation for the sigma algebra, and this is standard, and the sigma additive positive measure mu on this sigma algebra. And in general, we don't assume that mu is finite. For example, we can take the real line equipped with the Lebesgue measure, which is not finite. So we'll take a measure space, and let P be a real number greater than or equal to 1. And we introduce the following set, script LP of x mu. This set consists of those k-valued functions on x which are measurable and such that the absolute value of f to the power p is integrable with respect to mu. In particular, if p equals 1, then this is just the set of all integrable functions on x. The Pirkovskii inequality, which was already discussed in the case of Kn, has a natural analog for functions. And this inequality, the Pirkovskii inequality for functions, implies that, first of all, that script LP is actually a vector subspace. A vector subspace of k to the power x. And second, this space carries a canonical semi-norm given by the following formula. This is a semi-norm on the space. Well, the details are given in this exercise sheet. Actually, this is indeed an exercise which is not entirely obvious. But anyway, again, we take it for granted now. And, but by the way, if p equals 1, then this is indeed trivial. Because if p equals 1, then this is just the integral of the absolute value of x. And clearly, the triangle inequality is satisfied. Okay, so this is a semi-normed space. The natural question is it a norm? Well, in general, the answer is no. Let's observe that the semi-norm of f vanishes if and only if f vanishes almost everywhere with respect to the measure mu. This is a standard fact of measure theory. You probably remember that an integral of a non-negative function is 0 if and only if the function is 0 almost everywhere. So in general, this is a semi-norm. This is not a norm, but is a semi-norm. But we already know how to construct a norm space out of a semi-normed space. So by definition, the space big L P of x mu is defined to be the norm space. The norm space associated to script LP. So explicitly, we take the script LP space and we quotient out the vector subspace consisting of those functions which vanish almost everywhere. So formally, the elements of the big LP space are not functions, but they are equivalence classes. So two functions represent the same element of the big LP space, if and only if they agree almost everywhere. But nevertheless, it's a common abuse of language to call them just functions and to identify two functions if they agree almost everywhere. Usually, this convention doesn't lead to any problems. So where should I proceed here? Okay, let's now to define. So at this point, p is finite. P is greater than or equal to 1, but it is finite. Let's now try to define the big L infinity space. So what is the big L infinity space? Well, by analogy with the little L infinity space, it's natural to expect that the big L infinity space consists of equivalence classes of bounded measurable functions. In fact, this is not entirely correct. This is almost correct, but this is not entirely correct because a function which is equivalent to a bounded function is not necessarily bounded. So to define the big L infinity space, we introduce the following definition. We say that if we have a measurable function, suppose that f is a measurable function on x, we say that f is essentially bounded. Essentially bounded if there exists a measurable set E in X such that the measure of the complement of X of E is 0 and such that F is bounded on E. So f is essentially bounded if it is bounded on a set of full measure. Of full measure means that the measure of the complement is 0. And it's clear from the definition that this property doesn't depend, it doesn't depend on the choice of a representative from the equivalence class. In other words, if we have two functions which agree almost everywhere, and if one of them is essentially bounded, then so is the second one. Well, now we can discuss our last example for today, example 10. Example 10. We define the space script L infinity of x mu to be the space of all essentially bounded measurable functions on x. F is measurable and essentially bounded. Well, it's a simple exercise to show that this is a vector subspace. And this is a vector subspace of the space of all functions on x. And moreover, there is a canonical seminorm on the space given by the following formula. The notation for the seminorm is the same as for the supremum norm. But again, this is the standard abuse of notation. The definition is slightly different. So we do the following. First of all, we consider all sets of full measure, that is, all sets satisfying this condition, and take the supremum of f over each of them. So we'll do this for each set of full measure. And finally, we take the infimum. The infimum of this set. So this set is non-empty because we know that there is at least one set of full measure for which this supremum is finite. And then we take the infimum. It's an easy exercise, which is again included in our first exercise sheet, to show that this is indeed a seminorm. This is a seminorm on script L infinity of x mu. And there is a special name for the seminorm. It is the so-called essential supremum. The essential supremum of the absolute value of f. So sometimes this is denoted like this. So in summary, we see that the script L infinity space becomes a seminorm space. And similarly to the case where P is finite, we have this property. So the essential supremum of f vanishes, even only if f vanishes almost everywhere. And now we can construct the norm space associated to the script L infinity space. And this is the big L infinity space. So we define L infinity of x mu to be the norm space. The norm space associated to script L infinity. So more concretely, this is the quotient of script L infinity modulo the subspace of those functions which vanish almost everywhere. By the way, let's observe that the little L infinity spaces are actually special cases of the big L infinity spaces. So let's observe that for each p greater than or equal to 1, and including the case where p is equal to infinity, the little p space equals the big L p space on the natural numbers equipped with the counting measure. So here mu is the counting measure on the sigma algebra of all subsets of the natural numbers. The counting measure is just the measure which counts the cardinality of a set. If we have a finite subset of n, then mu of the measure of the set is just the cardinality, and for infinite subsets, it is infinite. So it's easy to see from the properties of the Lebesgue integral then these spaces are identical. Okay. So these are the basic examples of norm spaces. And let's now discuss operators between norm spaces. So we're going to discuss bounded linear operators. So bounded linear operators act between norm spaces, and I have already said that sometimes they are even more important than the space themselves. And from the viewpoint of category theory, bounded linear operators play the role of morphisms in categories of functional analysis. Okay, so suppose we have two norm spaces, x and y. And a linear operator t from x to y. So we have the following definition. We say that t is bounded. T is bounded if there exists a non-negative constant c such that the following inequality holds. For each element in X. Sometimes it is more convenient to give another but equivalent definition. And before we can do it, let's introduce some notation. So if R is a positive number, let's denote by Brx the closed ball of radius r, the closed ball in X of radius r centered at 0. Or sometimes we write just Br when the space X is clear from the context. Also, sometimes we will consider the open ball of radius r, denoted like this. This is the open ball of radius r centered at 0. And the sphere of radius r will be denoted like this. And now we have the following simple proposition. Suppose that x and y are normed spaces, and T is a linear operator from x to y. Then the following conditions are equivalent. Condition 1, T is bounded. Condition 2, T takes bounded sets to bounded sets. So for each bounded subset B of x, the image of B is bounded in y. Condition 3, T takes the ball, for example, the closed unit ball of x, to a bounded subset of y. And condition 4, T takes the sphere, for example, of radius 1, to a bounded subset of y. Well, the proof is very easy. For example, to show that 1 implies 2, we take a bounded subset B of x. So since it is bounded, it is contained in a suitable ball centered at 0 for some positive r. And so the image of B is contained in the image of ball of radius r. But if we now look at the definition of a bound operator, where is it? If we now look at this definition, we easily see that the image of the ball of radius r is contained in the ball of radius cr. Из первого А. Thank you. Well, so this is contained in the ball of radius CR, which is, of course, bounded. And so T of B is also bounded. Oh, sorry, this is just B, not bold B, but an arbitrary bounded set. An arbitrary bounded set. Well, clearly 2 implies 3 and 3 implies 4. This is clear. And finally, to show that 4 implies 1, we do the following. Well, since this set is bounded, we can find a constant C, a positive constant C, such that for each y in the sphere, the norm of T of y is less than or equal to C. And if we now take an arbitrary non-zero vector in our space, we can normalize this vector, that is to divide it by the norm of x. And this vector belongs to the unit sphere. So when we apply t to this vector, we get this. And finally, by the linearity of t and by the properties of the norm, we can multiply this by the norm of x, and we get exactly what we need. So this inequality holds for each non-zero vector in our space, but of course it holds for the zero vector as well. And so we conclude that t is bounded. Okay, let's now give a topological criterion for bounded linear operators. have the following theorem. Again, suppose that x and y are normed spaces, and suppose that T is a linear operator from x to y. Then the following conditions are equivalent. Condition 1, T is bounded. Condition 2, T is continuous at 0. And condition 3, T is continuous. And in fact, as we will see from the proof, we can replace here 0 by an arbitrary point at x. Well, let's show that, first of all, let's show that 1 implies 3. Well, indeed, to show that T is continuous, we show that T, well, it will be more convenient to show that T is sequentially continuous. So we suppose that xn is a sequence in our space X, which converges to little x. And we want to show that T of xn converges to T of x. Well, we just calculate the norm of the difference, that is the distance between T of xn and T of x. And by the linearity of T, this can be written in the following way. And now we use the assumption that T is bounded. So we substitute here xn minus x. And we conclude that this is less than or equal to C multiplied by xn minus x. And of course, this converges to 0. And this inequality implies that T of xn converges to T of x. And so T is continuous. Okay, now clearly 3 implies 2. This is obvious. And let's now show that 2 implies 1. So we assume that T is continuous at 0, and we want to show that T is bounded. Let's assume that T is not bounded. So we want to get a contradiction. Well, if T is not bounded, then there is no such constant C. And in particular, if we take an arbitrary natural number n, we see that this inequality fails if C equals n. In other words, for each n, for each natural number n, we can always find a vector xn in our space such that we have the opposite inequality. The norm of Txn is greater than n multiplied by the norm of xn. And to get a contradiction, we introduce a new element yn. We define it by the following formula. By the way, the number here is not 0 because xn, here we have a strict inequality. So in particular, this implies that xn is not 0. So we can divide by the norm of xn. So what can we say about this element? Clearly, the norm of yn is exactly 1 over n. And so yn goes to 0. On the other hand, the norm of T of yn, so if we substitute yn here, so what is this? This is the norm of Txn over n xn. And this inequality implies that this is bigger than 1. And in particular, this implies that T of yn doesn't converge to 0. And this is a contradiction. So we assumed that T satisfies condition 2, that is T is continuous at 0, and we said that this property fails. Yn converges to 0, but T of Yn doesn't converge to 0. And this contradiction completes the proof, so we see now that all the three properties are equivalent. As a corollary, we obtain a useful result, which enables us to compare different norms on the same vector space. So suppose that we have a vector space X. X is a vector space. And suppose we have two norms. Let's denote them like this. Norm prime and norm double prime. Two norms on the same vector space. And let's denote by tau and tau prime the respective topologies on X. I mean that tau prime is determined by the first norm and tau double prime is determined by the second norm. We give the following definition. We say that the first norm is dominated by the second norm and we use the following notation. If the topology determined by the first norm is weaker than the topology determined by the second norm, in the sense that we have this inclusion. And we say that the norms are equivalent if they determine the same topology. We say that the norms are equivalent if tau prime equals tau double prime. That is, if they determine the same topology on X. Well, now we have the following corollary from our previous result. Namely, I claim that the first norm is dominated by the second one if and only if there exists a positive constant C such that for each X we have the following inequality. That is, the first norm is dominated by the second one if it is less than or equal to the second norm up to a multiplicative constant. And as a corollary of one, as a special case, we see that two norms are equivalent if there exist two positive constants, little c and big C, such that for each element in our space, we have the following double inequality. So this is a useful criterion of the equivalence for two norms. Well, the proof is very easy. The proof is very easy. To prove the first part of this corollary, we consider the following operator. Let's denote this operator by big I. And this operator acts from X equipped with the second norm to X equipped with the first norm. And actually, this is just the identity map. So from the viewpoint of set theory, this is the identity map. But formally, we cannot call it the identity map because it acts between two different norm spaces. So the underlying vector spaces are the same, but the norms are different. So we have two different norm spaces here. Okay, so and let's now observe that the first norm is dominated by the second norm. If and only if this operator I is continuous. Well, indeed, this map is continuous if the preimage of an open set is open. In other words, this means that if a set is open in here, it is open here. It is tau prime is contained in tau double prime. Well, so we have this relation if and only if this operator is continuous. But we already know that this happens if and only if T is bounded. If and only if I is bounded. But this means exactly that there exists a constant C satisfying this condition. And that's it. So this completes the proof of the first part. And the second obviously follows from the first one. Just apply it to the first norm and the second one, and then just interchange these norms. So the second part follows from the first part. Okay. So our last result for today is to show that if we take a finite dimensional vector space, then all norms on the space are equivalent. So suppose that X is a finite dimensional vector space. Then any two norms on X are equivalent. In other words, this result implies that a finite dimensional vector space over the real numbers or over the complex numbers has a canonical topology, which doesn't depend on the choice of any basis, and which is determined by an arbitrary norm on the space. Well, to prove this result, without loss of generality, we may assume that X is just Kn, because each finite dimensional vector space is isomorphic to Kn. We take an arbitrary norm, and to prove this result, it suffices to show that an arbitrary norm is equivalent to the Euclidean norm. This will imply that any two norms are equivalent. And let's recall that the Euclidean norm is given by the following formula. Okay, so to show that these norms are equivalent, first so actually the proof will be given in two steps. So first we show that an arbitrary norm is dominated by the Euclidean norm. So let's denote by EI the standard vector in Kn of the following form. Here, the identity is in the nth position, and 0 is elsewhere. And we do the following. First of all, we observe that x. Oh, thank you, of course. N is the dimension. Thanks. N is the dimension, and I is the position of this this element here. Okay, so we now we decompose x in the following way, and we write the triangle inequality. We write the triangle inequality for this sum from 1 to n. And then we use the Pirkovskii inequality, which can be written in the following way. This is the Pirkovskii inequality. And this is a constant. We don't know the exact value of this constant, but this is a constant. And so we see that this is c multiplied by the Euclidean norm of x. And this chain of inequalities implies that our abstract norm is dominated by the Euclidean norm. Где? Одна вторая, thank you. Thank you. By the way, this is, this is exactly the Euclidean norm. Thanks. Okay, so an arbitrary norm is dominated by the Euclidean norm. And to prove the opposite relation, to prove that the Euclidean norm is dominated by an arbitrary norm, we do the following. We denote by f of x the norm of x. I mean, not the Euclidean norm, but the abstract norm of x. This is just a notation which is convenient for psychological reasons. And let's observe that f is continuous if we equip Kn with the Euclidean norm. I claim that f is continuous on Kn equipped with the Euclidean norm. Well, why is it so? Well, we already have this, this relation. So if I now calculate the distance between f of x and f of y, so this is the absolute value of the norm of x minus the norm of y. And the triangle inequality implies that this is less than or equal to the norm of x minus y. This is an equivalent form of the triangle inequality. But we already know that this is less than or equal to c multiplied by the Euclidean norm of x minus y. In other words, we see that f is a Lipschitz function. F of x minus f of y is less than or equal to this number. And this implies that f is continuous on Kn equipped with the Euclidean norm. Let's now consider the unit sphere. I mean the unit sphere centered at 0 with respect to the Euclidean norm. Of course, we know that this set is compact. With respect to the Euclidean norm. So it is compact and f is continuous. And this implies that f is bounded from below. So there is minimum. It is bounded and it attains its minimum on the sphere. And let's denote this minimum by little a. Well, let's now recall that f is not just an arbitrary function, but f is a norm. So it doesn't vanish. F doesn't vanish on the sphere. And so this number is strictly positive. And if we now take an arbitrary element, an arbitrary non-zero element in our space, we see that if we divide x by the Euclidean norm, then this vector will be on the sphere. So if we apply f to this vector, this will be greater than or equal to a. But what is this? This is exactly the norm of x, the abstract norm of x divided by the Euclidean norm of x. And finally, if we multiply this by the Euclidean norm, we conclude that the following inequality holds. And that's it. If we now combine this and this, we see that our norms are equivalent. And this completes the proof. So any two norms on a finite dimensional space are equivalent. And when you'll solve exercise sheet 1, you will see that for infinite dimensional case, this is not true. So there are many natural examples of norms on infinite dimensional spaces which are not equivalent. Okay, thank you. That's all for today. The next lecture, we continue our discussion of bounded linear operators, and in particular we construct some important examples of such operators.